Welcome back to another AP Pre-Calculus video. Today we'll be going over topic 2.6 on competing function model validation. So the first part of this worksheet is to graph these four tables and see if it is linear, quadratic, or exponential. So obviously we know that a linear is gonna show like a line, or it increases by a constant rate of change. We have quadratic here, which is always going to be like U-shaped, and it's going to have like a line of symmetry basically, and it goes from increasing to decreasing, or decreasing to increasing, so it changes basically. And then we have exponential here, which is the output values are increasing like proportionally. They're getting multiplied by a ratio, and usually it'll look like this. So we're gonna graph these. So first we have 0, 2, it's kind of 0, and then 2 is there, and then we have 3, 4, 3, 4. Now we're starting to get into decimal points here, so 5, 5.5, which is like between 5 and 6 here. That's a little bit higher, but yeah. And then we have 6, 5.75, so right here, a little higher than our previous one. Then we have 9 and 8.25. 25 is 1/4, so like a fourth, so like right there. And so it kind of looks like a line, right? So it looks like a line, and we probably know what the other points are gonna be on the left and right side. So this one is a linear graph. So our next one, let's plot these points. So we have -2 here, this is here, and 0.5 right there, and then 0 and then 1, so here. Then we have 2, 2, which is right here, then 5, 5.6, which is kind of above halfway, and then we have 7, 11.3, which is above the graph, but we know we can kind of predict where it is. And so we see here, it's not really a line. I mean, it can be, but because we have the option that it's exponential, it looks like it's going to be exponential because it kind of goes like that. And so it seems like it's increasing by multiplication, right? Because like if this is 1 times 2 would become 2, it only increase by 1. But if this is 2 and multiplied by 2 again, that's 4. It increased more than the previous one, even though we're still multiplying by 2. And 4 times 2 would become 8, and 8 times 2 would become 16. It increases differently, but it's still increasing by the same ratio. So this is exponential. Now the next one, we have here 1 to 9, so 1, 9 right here. Then 3, 7.1. Looks like this graph is decreasing. And then we have 5, 1. So 5, 1 is here. And then we have 7, 7.2. Okay, so now the graph seems like it's going back up, so it's changing the slope here. So that means we know it's probably a quadratic. Then we got 9 and 9.1. Yeah, so it looks like there's also like a line of symmetry there. And it's U, or like V-shaped. So that lets us know that it's quadratic. So this graph is quadratic. So let's plot the last table here. So we have -1 and 10, 2 and 8, 4 and 6.5, 7 and 5.1. And then we have 10 and 4. So 10 is like right here. And if we go up to 4.1, it's like right here. So this kind of looks like it's linear, right? But we can see like down here, they're kind of closer to each other than up here. So more likely gonna be a exponential graph. It seems to be multiplying by like a pretty low number, and that's why it looks close to a linear graph. So we're gonna say exponential there. Exponential. And if you still are mixed up or tied with linear and exponential, you can look at the table here, but make sure you're always looking at the equal length inputs. So we know this right here, these two are +3, these two aren't +3, so you don't want to look at those two numbers. These two are +3, and these two are +3 too. So we see this is whatever number it gets multiplied by. Don't check what this number gets multiplied with this number, because it's not x, or the input values for those two numbers aren't increasing by 3. What this number times this number is, and what this number times this number is, you can check. But yeah, it's like approximately 0.8, and clearly we see that like it's not linear. This is -2. This is less than -2, and this is -1. So now onto these questions. A quadratic regression was used to model a data set. This residual plot for the model is above right here. Which of the following statements about the appropriateness of this model is correct? If you don't know already, a residual plot is basically all the points of the residuals, and a residual is the actual minus predicted value. So I'll write that here, actual minus predicted. And an easy way to remember, I guess, is you can think of it as AP, since this is an AP class, but you do have to remember that there's a subtraction sign. And all these points are basically points of residuals, so they were points of the actual data minus the predicted, what you got, and then it gives us this number. And then we also know that if it shows a pattern, then it's not appropriate. The residual plot should appear without a pattern, and clearly this one right here, it has a pattern, so we know this is not appropriate. So we can cross off the ones that say it doesn't show a pattern. Like A, it says it does not show a linear pattern. Oh, that's true. But clearly this shows a quadratic pattern. So which one says not appropriate? So these down here say not appropriate, so we can cross off A and B. So quadratic regression is not appropriate because the residuals do not show a linear pattern. Well, if it doesn't show a linear pattern, it'll probably be appropriate for that linear, so it's not C. And now D, a quadratic regression is not appropriate because the residuals show a quadratic pattern, which it does. Also, we're looking for a quadratic regression here, so now here we have a table over the years 1950 to 2020. The total world population can be modeled by a linear function. Selected values for the world population P in billions are given in the table above, where T represents the number of years since 1950. So looks like the X value is T, and the Y values is the world population. So PT. And you don't have to write this, but I think it helps when you're writing the equation. So using the regression capabilities on your calculator, so we're going to pull up a calculator to find a linear model for the form of this for the world population in billions, X years after 1950. So let's pull up a calculator. Okay, so we have a calculator pulled up, and by now you should basically memorize how to do this. So math stat, and then click edit, and then put in your data values. L1 will be the X values, and L2 will be the Y values. So let's go ahead and do that. Then after you put in the values, go to math stat again, and then click, and then move to the calculator tab. Then go down to the regression that you are doing, which we're doing. A linear model has A first, or A plus BX. This one is AX plus B, so I'm gonna do A. Click enter and go down to store regression equation. We're gonna put, we need alpha trace to get that Y value. I'm gonna use Y1, doesn't matter, but, and then calculate. And then it gives us this, so we're gonna write that. So P of T we can write, which is basically Y, is equal to A, which is 2.26. Usually we want to round the third number, so we're going to say 8 there. You can put the entire number, I guess, since it's not that long, so 7.5. And then plus BX, which is 0. Now this is a long number, so let's round that. So 0, 7, and 8, and then X. So that right there is our linear model. Now B, according to the model found in part A, what was the world population in 1979, the year Mr. Passwater was born? So it's telling us the world population is 1979. That looks like it's 29 years after 1950 up here. And that must mean it's an x value or a t value. So that means that we can just put the 29 in there. We can use our calculator to find what p of 29 is, or in the calculator's case, y of 29, since we use y1. But also, you can also just do this by hand. You can plug in x for 29, so 2.2675 plus 0.078, and then plug in that x. You can do that if, I guess, calculators aren't allowed, but it should be since you used a calculator to get this equation, but I don't know. So let's alpha trace that and get that y, and parentheses to put in 29, and then that gives us 4.527 number. That should be the world population, about that, and world population's in billions, so it's about 4.527 billion. So we can say like about. So that's our answer. So what is the residual of the total world population for the year 1990? Which looks like it's 90 minus 50 is 40 years. So we can write down here 40. And did our model underestimate or overestimate the world population for the year 1990? We already see 40 years is on the table right here, so we're gonna highlight that. This must mean that this right here is the actual value, but we're gonna put it in our calculator here. So alpha trace line 1, and then plug in 40 to find out what our regression model gives us. So click enter there, and we get 5.385. We go round that there. So p of 40 gives us 5.385, but the actual here is 5.32. So the residual is actual minus predicted. So that gives us a negative number, since we're doing 5.32 minus 5.385. So that basically means a negative number means that we overestimated. But you can also just see it. Predicted is our predicted value, and this right here is the actual. Sorry for that handwriting. But yeah, we can see this number is bigger than this number right here. So basically we just we overestimated. So we can say this model, or our model, whatever, this model overestimated the total world population for the year 1990. So that's your answer. It's an overestimate. And what is the residual for the world population of 1990? It would be what this is. So let's put that on the calculator real quick. So 5.32 minus 5.385. That's the answer. So negative. It's around negative 0.065. But yeah, make sure that you're answering both questions. Okay, now, so our next question. A regression model was created for the data in the graph above. The residual plot for the model is given on the right here. Which of the following statements about the regression is best? So it looks like this. We can see this has a pattern. So then it's not appropriate. And we know the regression model is exponential here. So we can cross off A and B. So an exponential regression model was used, and the model was appropriate. The model's not appropriate, so it's D. It says not appropriate right there, because it does show a pattern. Okay, we see this one doesn't show a pattern here. Looks like, so he used a quadratic regression model. So we're looking for the quadratic model was appropriate because this displays the residual plot, displays no pattern. Why does it say A and A? C and D, we're crossing that off. It shows no, so it's appropriate, so our answer is A. Okay, so now looks like we have 3 models here. Okay, a set of data was used to create a linear, a quadratic, and an exponential regression model. The residual plots for the 3 models are shown above. Based on the 3 residual models, which of the following could be an appropriate model for the data? Appropriate. So we're looking for no pattern. This shows a pattern. This shows a pattern. Oh, looks like this one doesn't show a pattern. It's random, and we can't predict where the next dots are gonna be or the next points. So then we're looking for an exponential equation. This right here is not exponential. This right here is a quadratic, so it's also not exponential. Looks like this is exponential. And this one right here says log, so it's not exponential, it's a log graph. So our answer is C. Now, 10 and 11. Mr. Passwater loves to invest his money in mutual funds. Over the past 20 years, he has closely tracked how his account grows and noticed that each year his account grows by approximately 10.4%, which basically means that it's growing by a ratio, or it's growing proportionally, so it looks like it's exponential. And if Mr. Passwater wants to find a function that models the amount of money in his account over time, should he use linear, quadratic, or exponential model? Give you a reason for the answer. So we're gonna it's exponential. So an exponential model would be best because it seems to be growing. It grows by common ratio of 10.4%. You can just write 10.4 if you're writing percent, but if you're writing what you're actually multiplying it by, it would probably be 0.104, since you would move the decimal point when you multiply a percentage. So now our next problem. After Mr. Passwater creates his model for question 10, he used the model to create a residual plot in order to check the appropriateness of his model. If his model was appropriate, what should he expect to see when looking at the residual plot? So he wants his model to be appropriate, right? So that means that he doesn't want to see a pattern. I think that's all. So we can write his residual plot should show no pattern, no apparent pattern, no pattern if he wants his model to be appropriate. So yeah, he should expect to see no pattern on his residual plot. So that was 2.6, and hopefully that helped. Thank you so much for watching.